Voice of the Sea, learning from experts across the ocean.
Welcome to Voice of the Sea.
In this episode, we're mapping freshwater resources with the University of Hawaii's Ike Wai project. We'll meet up with scientist Henrietta Dulai in her laboratory to see how she uses chemical signatures to track the flow of freshwater underground and into the ocean. Henrietta's findings will help us map the location of freshwater and calculate the amount of water stored in underground aquifers. First, we chat with Gregory Chun from the Ike Wai leadership team to learn more about the importance of Hawaii's freshwater resources.
The intention of the program is to improve our characterization and our modeling of how water is captured and held within the geologic structure of the island and actually how it flows.
Is the amount of freshwater resources that we have available something I should be concerned about?
I think living on an island, and certainly with things like climate change and sea level rise, yes, we should all be concerned about it, particularly with increasing development pressures. Certainly we see that here on Oahu. Certainly we see that in parts of the neighbor islands, Maui, and even in Kona to a certain extent. But we also should be very open to the idea that we may not have a full understanding of really how much water there is there. And that's what this project is hopefully going to help us with.
And how might climate change or sea level rise affect our aquifer supplies of fresh water?
Well, certainly saltwater intrusion and inundation at the coastal areas does get into the aquifer. We know that you see that just with the tidal fluctuation. So if we're starting to experience sea level rise on a more permanent basis, you have to begin to question and wonder what that intrusion of salt water is doing. And given the importance of water, the sensitivity of water, and the breadth and depth of the community engagement activities of this particular project, I felt this was an opportunity to do community engagement differently. Particularly given that it's part of a research endeavor and not necessarily a development project, if you will. So we have a little bit more leeway in terms of how we do our outreach and how we work with our stakeholders than a developer might. So I'm really excited about building our knowledge base about community engagement and developing an area of scholarship around that.
You're watching Voice of the Sea. Today we're talking with researcher Henrietta Dulai in the Department of Geology and Geophysics at the University of Hawaii at Manoa. She uses radioactive signatures to trace where groundwater is coming from. We're going to go ahead and take a look inside Henrietta's lab.
We have several rooms here that are set up to do some wet chemistry. That means analyzing water samples and using acids in the fume hood. So that's our back room there. In this room, we have really a preparation before going out to the field, also preparing samples. We see a bunch of supplies here prepared for our field work. Once the samples come back, we process them here or in the next door lab. And then we have instruments right behind you. They are measuring mostly radioactivity. So we use radioactive isotopes like radon and radium that occur naturally in the rocks, and then the water dissolves them. And so specifically these instruments would measure radon.
What is radon?
So radon comes from the natural decay of uranium. Uranium is a natural element, isotope, decays by radioactive decay into certain different isotopes and eventually leading to radon. While uranium likes to stay within the minerals in the rocks, radon is a noble gas. It's a gas. It wants to diffuse out from the rocks. And if there is water around these rocks, then the water accumulates a lot of radon. That's how groundwater gets enriched in radon.
Oh.
But streams and the ocean has almost none of it. So that's why we can use radon as a tracer of groundwater.
So if you find radon in the ocean, that tells you that it came from the land.
Correct.
And so that's a place in the ocean where groundwater is coming out.
Exactly. So we create maps. We create radon maps of the coastal ocean that show the radon hotspots where we can tell, okay, this is where groundwater flows to the ocean.
And how do these instruments work?
So they are gas monitors, gas analyzers. So we collect water, as you will see today later in the field. We'll fill up bottles with water, groundwater and stream water, and we'll bring them back here and then strip the gas out of the water and pump it into these instruments.
Very cool.
And we have played around also with our tap water since we get our drinking water from the ground.
Oh, sure.
Our tap water has some radon, so it's natural.
Is it harmful?
Nope, it's low levels. If it was in much higher levels, it would be harmful. There are some states in the US that actually have to treat their water because it has high radon, but Hawaii has a really, really low radon, but still enough for us to use it as a tracer.
The University of Hawaii's Sea Grant College program, focused on Hawaii's coasts and its communities through sustainable development, safe seafood supply, sustainable coastal tourism, hazard resilience, and healthy coastal ecosystems. Hawaii's Sea Grant.
Welcome back. We're learning more about how researchers trace fresh water using radioactive isotopes.
So we also have some more instruments that are more geared towards radium isotopes. Similar story, radioactive decay in the rocks happens and then radium dissolves into the water, and we have different ways of measuring the different isotopes. So isotopes have different amounts of neutrons in their nucleus, and so they have different half-lives. Some decay faster and some shorter. And we can take advantage of that as a unique tracer from how far the water has traveled within the aquifer. So we also look at gamma radiation. That is also coming from radium isotopes. And that's the other instrument that we can look at. This is called the gamma spectrometer. And what it does is that same, we call it fiber, that collects the radium from the water, is first analyzed on that instrument, and then we put it out on this one.
That's the gamma analyzer?
Yes. So it measures gamma rays that come from two specific isotopes of the radium, and so we can really see the radium isotopes showing up on the spectrum.
And do you expect all three types of measurements to align? Or
yes.
to be different?
we hope that they align, but mostly we focus for the two longer-lived isotopes that are gamma emitters with the gamma spectrometry and two shorter-lived radium isotopes with the alpha measurements.
But all three instruments are trying to tell you where groundwater is coming out into the ocean.
Correct, yes, and how much. We also try to quantify how much, and the radium isotopes actually even can tell us the flow path, which way the groundwater traveled underground based on different kinds of rocks that it went through that collected different radium signature.
Oh, wow.
So that's the hope for the Ike Wai project, that on the Big Island, where we have convoluted groundwater flow paths and some confining layers that don't let water interact fully with the aquifer, that we will be able to say something about those flow paths in Kona.
And so I understand that the aquifers in Kona, that there's maybe some high-level aquifers and some base-level aquifers, and you want to know where the water's coming from and if those high and low-level ones are coming together.
Yes, correct. We want to see whether the high-level aquifer feeds any of the basal lens. And it's suspected that it is. Some isotopic data already suggests that. But then also we are collecting water samples along the shoreline, seeing which chemistry it matches, the high level or the lower level, or is the mixture, and then what ratio. We want to understand where the water goes, how fast it flows, how much of it stays underground, so we can tap into it as a water resource. It also feeds our streams. We want healthy streams.
What about in terms of health of the water itself? Is that part of what you're looking at?
That unfortunately is a big piece of it now, because we find pollution going into the ground, into the groundwater, and so we find septic signatures, we find agricultural, like fertilizer signatures, pesticides, that we would think that out of sight, out of mind, but unfortunately it is traveling with this groundwater flow into the streams and the coastline. So specifically at the coastline, we see groundwater that discharges right onto the coral reef that brings those pollutants with it. How big of a problem that is for the reef itself, it's still yet to say, because groundwater flow occurs over larger areas. It's not one concentrated source like the streams would be. And so perhaps that gets diluted enough, but yet we do see impact on some of the shorelines.
So I was thinking that groundwater would be flowing into the streams and that that's where you'd be measuring it. And it sounds like I'm not correct. So how is groundwater coming up into the ocean?
Groundwater flows out as springs or diffuse sheet flow along the shoreline, all along the shoreline. In fact, our research has shown that for every whatever stretch of the coastline or embayments you look at, there is at least as much groundwater flowing to the ocean as is stream water. I guess I should point out that, so we collect many gallons of water in the field, and who wants to get it all back to the lab? So all we do is we concentrate the radium and the radon, and so specifically the radium isotope eventually gets concentrated from many, many gallons into this small sample.
Wow.
that we then analyze. So these are our little samples that hold all the radium there was in many, many gallons of water.
And how do you concentrate it down?
You will see in the field.
Okay. I have to wait. And is it dangerous for me to hold this?
No, it is the same as you would be swimming in the ocean, where you are surrounded with a large volume of water also. So all these radioactive elements are there naturally. It's not an added tracer, and our bodies have accustomed to some level of radioactivity that surround us. So I consider this as part of that natural background. So this is our gamma spectrometer, and as I said, from the many, many gallons of water, this is where radium is all concentrated out. And so that's analyzed by this gamma spectrometer, and the peak that comes up is from the radium. So this sample has been now measured for 2 days. We definitely collected enough counts to analyze it. So I'm going to stop this measurement.
Why does it take 2 days to analyze it?
Because it takes so long for so many atoms to decay, so we collect enough to actually identify the peak above the natural background.
So it's decaying while it's in there and
Correct.
you're measuring it?
Correct, yes.
But you're not speeding up the decay. That decay would happen naturally.
Nothing can speed up that decay. Correct, yes. Radioactive decay is pretty constant. It's a statistical event, but it's a pretty constant rate, very constant rate, actually. We have atomic clocks running by radioactive decay. All right, so I saved our old sample, and I'm going to change it now. So you can have a look into a gamma spectrometer that has a germanium crystal that's surrounded by lead. The lead filters out all the radiation that's coming from the walls.
Oh, wow.
So we will take the old sample out and put the new one in. And
It's
so
kind of beautiful in there.
it's a cadmium-lined lead, so it filters out all the radiation coming from the walls and the air.
Oh, and it's hard to close.
It's quite heavy. We have a special enforcement on the ground.
And then this will take another 2 days
2
to
days,
run.
yes. We run them at least 2 days, sometimes longer, depending on whether they have enough of the signature.
So I see a large box of samples to run and a large box of samples that have already been run. And if it takes 2 days, you're only running like 170 samples a year,
Correct.
possibly.
Correct, yes.
Wow.
Yes, so we have sampled maybe 30 wells on the Big Island that we just finishing up measuring. This happened actually during previous years of many years of projects. And so we never got a chance to fully analyze the data. And so now is the chance with this new project that we can actually use these and say something about the groundwater flow paths.
The Curriculum Research and Development Group in the College of Education at the University of Hawaii at Manoa. CRDG's training roots go back over 40 years. Through professional development programs, curriculum workshops, research on teaching methodology, individualized school and district training, and so much more. The Curriculum Research and Development Group, improving schools, improving education. CRDG.
Welcome back. We're talking with geochemist Henrietta Dulai about her work on the Ike Wai Water Research Project.
I grew up in Central Europe, and I grew up every summer spending on the river, and we have a couple of lakes, but it wasn't until I turned 20 years old that I saw the ocean, and it captivated me right away. And so ever since, I have been working in an ocean environment and coastal environment. What really motivated me was that it was so much fun to go out on the ocean to collect samples and interact with other people, and really delving deeper into, okay, what's in the water? That has always been a natural curiosity. So just beyond going out and hanging out looking at dolphins and fishing, we actually collect samples and get to spend time going out to places, visiting places, and working with local people and learning from them about the ocean. That has always been so cool. So not just going as a tourist, but going as a scientist and getting to work with the local communities and learning their perspectives. That has always been fun.
Your instrument is called a sniffer.
It sniffs for radon. Radon is a gas, so we gave it a name, and it looks like a doghouse. We pretty much made a portable gamma spectrometer that we can then deploy out at the coastline, and it can do hourly measurements of radon because it's surrounded by so much water, by volume, that we don't have to concentrate anything, and so it's just pretty much this hourly measurement. Groundwater flows out from the land to the ocean thanks to this difference in the hydraulic head. So the water level in the ground is higher than in the ocean, therefore it flows by gravity. Now this change in the hydraulic head changes with the tide. With swell events, also with seasons. That's exactly what we want to capture. You see that over time, the green representing the average changes, so these might be rain events or swell events. And then when we zoom in into this little hourly time scale, we see that at every high tide, the groundwater discharge stops, and at low tide, it accelerates. So most of the groundwater discharge pulses with the tides, and we see a lot of discharge happening at low tide, so the tide is indicated by the dashed line. And the radon concentration, therefore also the groundwater flow, is the solid line.
And that's because at the low tide, the difference between the groundwater and the seawater is greater.
Correct.
And then at high tide, they're closer together.
Yes. And so even sometimes the tide, or if there is a swell event, that might be above the water level, so it might completely stop the groundwater flow to the ocean. And so this tidal signature has been known for years, but what we really want to look at, or what this unique instrument allows us to do, is to look at seasonality, even the sea level rise trends, whether they make a difference on how much groundwater discharges. And then also, we want to know then what is more important, the rain events or the ocean sea level changes to the groundwater flow. And so this is relevant because understanding this will allow us to learn more about the aquifer itself. So for Ike Wai, that's the important part. What do we know about the aquifer, how its properties change, how much water leaks out of it? It's pretty much, imagine as a box that's filled with water, and then the water level within it will depend on how much you put in and what comes out. So rain puts water in, and then from the aquifer we pump water, and the other output is then leakage to the ocean. So once we understand the leakage out to the ocean, we can understand more about the box itself. So we can learn how the aquifer behaves with respect to sea level changes and also precipitation changes that's supposed to change in the future due to climate change. Now, how much can we take out is the big question. That's what all we would like to know, because it's our resource that we depend on. And again, understanding what leaks out of the aquifer helps us put that puzzle together. People living along the coastline used to use springs, even coastal springs, as their water supply. They use these natural springs and alkaline ponds that are openings into the aquifer right at the shoreline.
What is an alkaline pond?
The alkaline ponds are water bodies that are small ponds that are fed by groundwater, but they are close enough to the shoreline that they are also affected by the tides, so they have brackish water. Some can be fresh, some can be completely salty, and so they are right at the interface of the fresh water and the ocean water meeting, and so they have very unique ecosystems, and they are also culturally very important. So for this new Ike Wai project, we are building 2 more instruments like this, and I'm hoping to put some of them into alkaline ponds so that we understand more about this dynamics of fresh water fighting with the ocean tides, and then also inform us about groundwater flow out to the ocean and what sea level rise will do to the ponds.
So will you simultaneously have the instruments in the alkaline ponds and out in the ocean to compare?
Yes.
Really cool.
We already have one instrument. So this one was deployed in 2014 in Kiholo Bay, which has large amounts of groundwater flowing into it. And we can now look at that data set. We have early measurements over 3 years, and so we can already look at some seasonality. But we don't have any information yet on the ponds beyond salinity. And so this will really be a unique data set to look at. And so I'm hoping that all this data that we are collecting is not just for our own enjoyment, but will be used in a hydrological model that my colleague is putting together. So this will be one of the inputs to his water budget. Mm-hmm. And again, so that's the bigger picture. We want to provide as much information as we know about the aquifer so that he can take this information and build a good water budget for the islands.
And then I imagine it's also applicable once you guys are sort of satisfied with your model here in Hawaii, you can take your tools and use them on other volcanic islands?
That is correct. That is the hope. Yes, yes. So we develop the knowledge and then the know-how. What is it that we really need to know? The essential information. And then that can be applied to other places.
Exploring Our Fluid Earth is a dynamic curriculum developed by the University of Hawaii's Curriculum Research and Development Group, teaching ocean science concepts through the disciplines of physics, chemistry, biology, and ecology. Exploring Our Fluid Earth is now available freely online. Find out more at exploringourfluidearth.org.
The University of Hawaii Sea Grant College Program, helping coastal communities of Hawaii and the Pacific through research, education, and outreach. Serving the community from elementary to graduate students. Hawaii Sea Grant.
Island Earth is working to establish new avenues for connecting research scientists with educators and communities. Kosi Island Earth is working to enhance the science and ocean literacy of our island residents and visitors. Kosi Island Earth is working to connect scientific research, traditional knowledge, and ocean policy. Kosi Island Earth, bringing together university, government, research, and community partners to enhance ocean literacy and engage all ocean users in stewardship.